Assalamu alaikum. In today's video, I would be discussing about how you can create the geometry with the help of atoms, with the help of LAMMPS, so that you can run the simulations on that geometry. So previously, I have been explaining the code of crack propagation, and in today's snippet, we would mainly be discussing the geometry portion of the code. So firstly, you can see that there is a command create geometry. Next, you will see the line lattice hex 0.93. So what does this mean? So lattice usually means that you define the points in space where your atoms would be located. So plain and simple. For example, here it's hex. Hex means a hexagonal arrangement. So you define these points, and the 0.93 means the lattice constants, so which usually means the distance between the atoms. So with the help of this, you have defined your lattice. The next your next work is region box block. So what this region does is, this region takes a space, a geometrical space where your simulations would be run. So by block, it means that, for example, let this be your coordinate axis, and in this axis 0 to 100 means along the x-axis, 0 to 440 means along the y-axis, and minus 0.25 to plus 0.25 means the z-axis. So firstly, for the x-axis, let 0 to 100, y-axis 0 to 40, and the z-axis minus 0.25 to plus 0.25. So ultimately, your block would look something like this. So this would be something like your block, and this box here, we are naming it box. This is the name of our region. Next, you see create box. So we have already created a box. Then what does this create box mean? So the create box is, what you have done up until now is you have defined a geometric region. You have not yet prepared it for a simulation. So to prepare it for a simulation, this create box command is used. What it does is, it divides this region into particular subdomains for simulation. So it defines these regions. Moreover, it also assigns a processor to a particular subdomain. So it helps in computation, it helps in parallel computation, and all these things is done by the create box. So you see there is a 5, which means there are 5 kinds of atoms here, or 5 elements here, and the box means we are doing all this for the region box. Next, you see create atoms. So you have already determined your lattice points where your atoms would be placed. You have already defined your region. You have already divided your region by using the word create box. All that's left is for you to place your atoms, and this work is done by create atoms 1 box. 1 means of the atom type 1, and you are placing it in the region box. Then you see the mass. So by mass, you are indicating that you have 5 kinds of elements. This one is the atom ID type, and the 1.0 is the numeric value of each ID type of, for example, the one element has a mass of 1.0, the second element also has a mass of 1.0. So what we are doing here is, we are actually using one particular element, but we are also saying about 5 different kinds of atoms, mainly because it will help to divide our space or region into several domains or regions, which would later help us with visualization and for some parts of the simulation, which I would show in the later videos. So I am going to delve deeper into each of the codes here. So firstly, lattice. So you see, in LAMMPS, a lattice is simply a set of points in space determined by a unit cell with basis atoms that is replicated infinitely in all dimensions. The arguments of the lattice command can be used to define a wide variety of crystallographic lattices. So you see that firstly you are using lattice, which means you are defining the points in which the atoms will be generated. Then you are using the style. So the style may be from a lot of options. You have no style, simple cubic, body centered cubic, face centered cubic, hexagonal close packing, diamond, squared, hexagonal, custom. So you need to keep in mind that HCP, hexagonal close packing, and hexagonal is not the same thing. So hexagonal close packing means the atoms are in a hexagonal arrangement, alright, but there is a particular arrangement of stacking of one layer above another layer which is not present in case of hex. Okay, so next you see that scale. So scale usually means or indicates two things. For example, the scaling can be between the lattice and the simulation box. So you might indicate a scaling factor which would indicate how bigger your simulation box or your lattice is with comparison to the other. And for our case, we would be using the scale to define the lattice constant or the lattice parameter, which you see here is 0.93. So you can include some other keywords also. For example, the origin spacing, or A1, A2, A3 basis. So some of the words might go over your head, so I'm going to delve a little deeper. For example, firstly, the purpose of the lattice. So you understand that the lattice command is used to define the arrangement of atoms. The lattice styles are the styles I have talked about so far. For example, for cubic, you can use simple cubic, face-centered cubic, body-centered cubic, diamond. You can use HCP, you can use square 2, you can use custom, customized style. Then the unit cell and the basis atoms. So I have been using this word a lot, basis atoms. What does it mean? So for example, this is your unit cell and these are the positions of the atoms within the unit cell. So these positions are, or these atoms which are located within the unit cell, can be called as the basis atoms. Okay, so next, the transformation parameters. So you can transform your lattice by different parameters. For example, you can use scaling factor to scale it larger or smaller. Then you can use origin to define the origin of your lattice within a space. You can use orient to rotate, effectively rotate your lattice. Then there is the part about dimensionality and compatibility. So you need to keep in mind that, for example, at the beginning of this code we have used the code dimension 2, and in the later part, while creating your geometry, if you say that your geometry is HCP, which effectively means that you cannot make it a 2D material, so it is not compatible with what you said earlier. And you need to keep in mind that this dimension which you are working with is compatible with the first part of the code. Next, you find lattice spacings. So lattice spacings is mainly in the XYZ direction, the lattice and the distance between the units. So next, you find customization. So you can you as a user can define your own customized cells with the help of arbitrary edge vectors and basis atoms. And lastly, the usage in input scripts, which you have gone over a lot of times. Next, you find region. So what's region? Region is a geometric region of space which can be used for the simulation. So how do we use the syntax for it? Firstly, we use the keyword region, then the box. The box is mainly the name of the region. Okay, next, this full is our style. So we have used the word style box, style block, and whenever you use the style block, you need to also mention these 6 arguments, that is x low, x high, y low, y high, z low, z high. if you would have used any other region, any other style. For example, you are using cone like this, you are using a cone. In that case, you might need to use the radian, low, radian, high, low, high, etc. For example, you are using cylinder, then you need to use C1, C2, radius, low, high. So there are a bunch of styles, and for a particular style you need to use the particular arguments. So what is the purpose of this region? Easy. You are defining a special region within a simulation box. Nextly, the usage. So the main reason of this region is that this region is typically followed by a style keyword which defines the kind of space you are using. For example, it can be a block or sphere or cylinder, etc. Then it can be a static or a dynamic region. So what does static region mean? Static region means that your region does not move along with time. So if in our case you need a region that actually moves with time, you can use the keyword move or rotate, which would help your system to move with time. Next is the deletion of regions. So if you want to delete a previously defined region, you can use this keyword delete to delete previously defined regions. Next, you can use the boundary conditions. So why do we need to use boundary conditions again? So for example, you have defined your region as block, and you want to make a particular end of your block free or fixed. For example, you want to fix this part so that no atoms come out through this particular wall. So you need to fix this wall or region. So this boundary conditions helps you in that regard. So you can use fix wall or region to fix a particular portion. Then you can use open region. So on the other hand, if you want to open this region, for example, this is totally open for like a funnel or something, so you can use the keyword open to effectively open a particular portion of your region. Then there is the part about units and scaling. I've already defined dynamic properties. Okay, so this is an important aspect of region, union and intersection of regions. So for example, you need to create a complex geometric shape, and to create that complex geometric shape or region, what you can do is firstly create a simple geometric shape, and then you can use the union or intersection to create a complex geometric shape. For example, let you want to create a duck. So what you can do, firstly you are creating an oval here, you are creating an oval here, and you are doing this, and you are doing this, you are doing this, you are doing this. So this is your duck. Sorry, that was a joke. Okay, so this is all for the regions. And then you have the create box. So what does the create box help you in? So you have already defined the points where your atoms would be generated. You have defined the region where your the region, like the box, the block, the cubic, etc. The box helps you in dividing the region into subdomains so that it will help in case of simulations. It also assigns a processor to a particular subdomain. So all the simulation stuff is completely dependent on this create box. So the syntax is create box. This 5 indicates the number, you see, number of atom types used in the simulations. So for this simulation we are using 5 types of atoms, which are effectively the same, but we are using 5. So this is the 5, and the region ID, we have named our box. So this is the region ID, and you can use extra keywords here like this. You can define the bond type, the angle type. You can also define extra bond per atom value, etc. So these are all high-end stuff, and we will come to those later. So in case of box, you can understand the main purpose is to establish the simulation domain, and the region needs to be defined earlier. You cannot create a box if the region is not defined. Next, all we have been working with till now, like the cubic shape, is effectively a orthogonal simulation domain. But if you need to create a simulation domain which is non-orthogonal, for example, the simulation domain is like this. So in that cases, normally prism region, for example, if the region is of style prism, then the create box domain, simulation domains also need to be non-orthogonal. So in those cases, there are certain other factors which you might need to consider. For example, there is the restraint of the constraint of the tilt factor. The constraint of the tilt factor is this, that the box cannot skew more than half of the distance of the parallel box length, and there is also the factor of tilt. So you need to consider the performance in case of creation of the box, because it is important that if the atoms you are planning to simulate is much smaller than the region you have assigned it to, so actually you are wasting a lot of space and effectively computational resources. So you need to consider all this in case of creation of the simulation box. Okay, so the main restriction is you need to define the atom style and region before creation of the atoms. So finally we have reached to creation of the atoms. So creation of the atoms means you have, so up until this point what we have done, we have created the lattice which determines the positions where the atoms would be generated. Then we have created a block saying that this is the region where our unit cell would be. Next we have used create box, which effectively helps us in dividing this block into subdomains for simulations. And finally we have reached the create atoms. So what this create atoms does is it creates or generates an atom in the particular positions earlierly defined by the lattice. So how does it does this? Create atoms. One is the type of atom. So we are using only type 1 element of the 5 types of elements we have to generate atoms in these positions, and we are using box. So what does this box mean? Box, for box no arguments is required, and this is our style. You need to understand that this is not the variable we have been using up until now. This is the style of how we are placing or generating our atoms, and there are other styles as well. For example, region, there is single, there is mesh, there is random, and all the styles. And there are also keyword values. For example, if you want to define the basis, if you want to define the fraction, the ratios, and all that stuff. So creation of the atoms, firstly the purpose, it generates atoms. There are styles which I've been saying up until now. The styles mainly hold like box, which we have used up until now. It means that we are filling the entire simulation box with particles on a lattice. Okay, so we can also use region. So what does this region mean? Region fills a geometric volume defined by region with particles on a lattice. Okay, so next we also have single. So single means we are generating a single particle at very specified coordinates. We have box, we have region, we have single, and then we have mesh. So mesh indicates that, for example, in a triangular mesh by an STL format, so you need to use mesh to place particles there. Then you have random, which is very important because in case of amorphous materials, the atoms need to be in random spaces or random positions, and in that case the random style helps a lot. And finally you have molecules. Okay, in case of options, you have a lot of options to choose from. Firstly, overlap. So what overlap helps is in preventing the newly created particles from being too close to existing particles, which is very important because of the potential and all. And then you have max tree. So the max tree, it helps in limiting the number of attempts to generate valid coordinates for a single new particle. Okay, and then you have remap. So what is the use of remap? So if in some case any atom or any particle is generated outside the simulation box, it helps in mapping that particle back into the box, assuming that the periodic boundary conditions is applied. You will see the use of remap in the later codes. Then you have rotate. So if you need to rotate the orientation at which the molecules are inserted, then you can also use rad scale, which mainly adjusts the radius of the created particles in the mesh style. You also have ratio, you have subset, you have var and set. Okay, so functionality. So atom IDs are assigned consecutively following the largest atom ID existing before the command was invoked, and all that. Considerations. So in case of consideration, you might need to use this a lot. So delete atoms, what this does is, sometimes when you are generating new atoms, you might generate an atom or a particle over an existing particle or atom, and in such cases you need to delete atoms. Moreover, this also occurs when you are minimizing the energy, you are doing any other function, doing any other operations, and your atom might go one above another, and in such cases you need to delete atoms. Okay, so the restrictions are mainly that atom style needs to be defined and all that. And finally we have mass. So this is a pretty straightforward in the basic sense. For example, if what we are doing here is defining the mass for every element we have used. We have used 5 elements here, and for the first element the mass is 1.0, for the second element the mass is 1.0, and it follows in the same procedure. So thank you. This would be all.